Welcome to the next class, next video lecture. So today we will start microwave devices. In that we will try to first of all do those devices which are different from the conventional devices. So one of them is transport electron devices, and how they are different from conventional devices is their main property is the property of negative resistance. Okay, we will see what it means. And the other important property of these devices is that they are not junction devices, unlike diode or transistor where we have junctions NP, PNP, and unlike MOSFETs where we have gates. What they are bulk devices. So whatever material is used, there is throughout one material. Okay. The other important difference is with respect to material itself. Usually transistors are fabricated from silicon, germanium, okay, and so on and so forth. But TEDs, they are fabricated from compound semiconductors like gallium arsenide and indium phosphide, cadmium telluride. Another difference, what differentiates TEDs from the usual microwave transistors is that the transistors operate with something called warm electrons. These are the electrons whose energy is greater than or equal to, is not greater than thermal energy, is less than that. You know, thermal energy is at room temperature 0.026 electron volt, whereas TEDs operate with they are called hot electrons. Okay, why they are called hot electrons is their energy is much greater than this thermal energy. Okay, ET. So hence the theory used to understand the transport electron devices is completely different from the usual microwave transistors. So the reason I will not cover microwave transistors is, if you know the usual transistor, it is not difficult to understand microwave transistor. But TEDs have a different theory which we will explain. One of the important developments in TEDs is the invention of Gunn Diode in the name of a scientist J.B. Gunn in 1963. Okay, so there is an effect which is called Gunn effect, and they are fabricated using gallium arsenide. So you can call them gallium arsenide diode. But again, a warning that it is not a usual diode. There are not two junctions. It is a whole bulk. The whole bulk is made up of gallium arsenide. And these diodes are used for amplification purpose. So for low power microwave applications, you can use Gunn diode instead of Electron. But again, for very high power, we can't use Gunn diode. We have to use Electron. So one is amplification, and most importantly, the oscillator, microwave oscillator. And both amplification as well as the oscillation application, they are derived from the same property which I told, the negative resistance property. That property is used to use Gunn diode as amplifier as well as for oscillator. Now the first question is how to achieve this negative resistance in any device. So three engineers, scientists, they worked independently over the problem. One was, in fact, two were Ridley and Watkins, and independently the third one is Hilsum. So they developed a theory that how we can fabricate the devices which can have negative resistance property. For this reason, the mechanism, the theory behind this is called RWH, Ridley-Watkins-Hilsum mechanism or theory. We will see in detail, but we can say the summary of the story is, you might have seen two bands in the usual energy band diagram, the conduction band and the valence band, and there is energy gap in between. In those devices where we want negative resistivity, there is not a single conduction band. So there are these satellite bands also, and here is a valence band. And it is because of these satellite bands that we can have negative resistance, which we will see how. Okay, so the main this RW mechanism, what they did is they studied those solid state devices, solid state materials, by which we can have these satellite bands, and how they can be utilized to get negative resistance. Then this effect was studied in detail for gallium arsenide by J.B. Gunn, and he actually you can say then fabricated a first bulk gallium arsenide diode. So J.B. Gunn first published his observations of experimental results. So I will directly, instead of writing it here, I will copy paste the exact wording which he published in the paper, which is in the book also. Here is on the right hand side, this is the picture of, you can say, schematic of Gunn diode. You can see there is a single bulk device here, single bulk device, and its anode, and we have here metal coated contact, so there is no p-n junction. Okay, so what J.B. Gunn observes is that when we have very high electric field, maybe in the range of 2000 to 4000 volts per centimeter, then the current becomes fluctuating function of time. This is for gallium arsenide sample, and the oscillation, the frequency was mainly determined by the Spiceman, not by the external biasing circuit. And the oscillations were proportional to the length of Spiceman, length of this gallium arsenide, and it was closely related to the transit time of electrons between electrodes, how much time it takes. And you can see that 1 gigacycle per second and 3 gigacycle per second, such very high frequencies were generated via this Gunn diode. This was experimental study, and now we needed a solid theory for it. So as explained already, that theory is called Ridley-Watkins-Hilsum theory, and the model is also called two-valley model. We will concentrate on gallium arsenide, and here is how the electron energy band diagram looks for gallium arsenide. This is the energy band diagram for n-type gallium arsenide Spiceman, and the various factors you can see. First of all, it has usual valence band here and conduction band, and then it has two conduction bands. You can see that the mobility of electrons in this conduction band is 8000 centimeter per volts per second, and mobility of electrons here is 180 centimeter square per meter second per volt second. So we call this as low mobility valley, and this as high mobility valley. The energy gap between the conduction band, that is the first low mobility valley conduction band, and the valence band is 1.43 electron volt, but the energy gap between low mobility valley and high mobility valley is 0.36 electron volt. We can also see that effective mass is having reverse effect. If you, the prerequisite for this gallium, this Gunn diode is you must be knowing electronic devices basic concepts. So the effective mass, we will talk in terms of effective mass. So here the lower valley, the electrons have effective mass less than the upper valley. Okay. Now if you denote by NL and NU the electron densities in lower and upper valley, and similarly corresponding mobility by mu L and mu U, then we know that the conductivity will be the charge E times mu L NL plus mu U NU. Now we know that when when electric field will be applied to this gallium arsenide bulk material Spiceman, the electrons will gain velocity, they will be accelerated, and their conductivity, or you can say first of all their mobility and density, they will be function of electric field, they will change electric field. Sorry. So we differentiate this conductivity with respect to electric field, we get. So we apply UV formula to this equation. So E times mu L dNL over dE plus mu U dNu over dE, then again plus E times, then we keep N fixed and differentiate the mobilities. Okay, we get this. Now what is the total electron density? The total density will be NL plus NU. Let's call that as N. Okay, and one assumption is made here, which is experimentally validated also, that the the mobility is proportional to the pth power of electric field. P is some constant, so both mu L and as well as mu U. Okay, so now the total density remains constant. Lower value and upper value density will change, but total density remains constant with respect to electric field. Okay, because see what happens is, when we apply the high electric field, electrons may jump from lower value to upper value. Okay, so NL and U will change, but total density will definitely remain same. So differential of N with respect to electric field is 0, which means that dNL over dE, hence dNL over dE is minus of d and U. Okay, and we assume that this mu is proportional to e to the power p, so it means that d mu over dE will be proportional to dE to the power p upon dE, which is p e to the power p minus 1. Okay, which we can write as p e to the power p divided by e, right? But this e to the power p is again proportional to mu, so we can write this is proportional to p mu by e, and hence we can write as mu p over e. So we call this equation as 1, this as 2, and this one as 3. Okay, now we substitute 2 and 3 in 1, we will get what is in 2, d sigma over dE is equal to E times. Now this dNL over dE remains as it is, so I will write here mu L dNL over dE plus mu U, then dNU over dE can be written as minus of dNL, so I will write here minus dNL over dE plus E times, now NL, and this d mu over dE can be written as mu E by P, so I will write mu L, P is constant, divided by E plus NU mu U P divided by E. Okay, I have just used these two relationships, I will now rearrange. This is what we got now. Okay, call this as 4. We also know that current density is related to electric field in this way, where sigma is conductivity, and this is also another way of writing Ohm's law. Okay, so we differentiate this with respect to electric field, so we get dJ upon dE is simply sigma plus d sigma upon dE times E. Okay, using UV formula, I can divide by sigma on both sides, I will get, let me call this as 5. Okay, now this equation is very important, this will provide us the explanation for negative resistance. Just recall that usual semiconductor materials, if you plot this JE diagram, current density electric field, you will see that the slope usually is this positive, and the slope of this JE curve is the resistance. Okay, and you know that its slope is always positive. But what we want bulk materials with negative resistivity, so it means that their JE plot should be something like this, or in other words, the slope of JE plot should be negative when we want the negative resistance. Hence, it means that this differential dJ upon dE, this should be less than 0 for this bulk material to have negative resistance. Okay, negative resistance. And see the important thing, this we are able to write only because there are two values, lower value and upper value. The equation has this form. If there were no two values, you could not get this form. Hence, if any semiconductor material which doesn't have two value satellite values, okay, in the conduction band, they will not exhibit the negative resistance effect. So now this can be also written as alternatively that d sigma upon dE, okay. So I need this to be less than 0. So in other words, this quantity should be less than 0. So I can write d sigma upon d divided by sigma by E should be greater than no, not greater than, less than minus 1, or in other words I can write minus of this should be greater than 1. Okay, so this is the condition for negative resistance. Now I recall some equations. One is about the conductivity, and the other equation we just now got, I will again write it here. Okay, these two equations, and using these two equations we can substitute the value of d sigma over dE and sigma by E here, and we will get the condition. So this is the condition after substituting these two values, dividing the denominator on both sides of numerator, we get easily this equation. Oh, one typo, this sigma is not there. Okay, just erase it. Sorry, sigma is not there. I can rewrite this equation in this form. Okay, just I have clubbed up this E and D and L upon dE and written minus here, and it's P. Now I define F as a fraction of electrons in upper valley divided by the number of electrons in lower valley. It's a fraction of electrons. Okay, so after putting that, I can divide this by NL, okay, on both the sides, numerator and denominator. I will take NL common here in the denominator here, so I will get this condition. This is the condition in terms of mobilities of electron in lower and upper valley, in terms of fraction of electron in upper and lower valley, number of electrons and electric field, and how number of electrons in lower valley vary with electric field, and P the constant. This is a relationship which will guarantee that the bulk device will exhibit negative resistance. This P definitely depends upon the property of the solid state. So in particular it depends upon the scattering mechanism in the rates. Okay, so scattering mechanism definitely, because you see how this mobility, how conductivity will vary with electric field. That definitely depends upon how electron will so it will get accelerated. But what is the lattice mechanism? Is there any scattering of electrons when they are getting accelerated? That scattering mechanism will definitely affect the conductivity of electrons and the variation of conductivity with electric field. So P depends upon the scattering mechanism, and preferably it must be negative. You can see the structure of this equation. This P must be negative and large. Now let's analyze this equation. See what we want. We want this whole thing to be greater than 1, right? So if you see properly, the first thing we observe is this mu L should be greater than mu U. Okay, because only when this term is positive, and definitely when you apply electric field, electrons will move from lower valley to upper valley. So the number of electrons in lower valley will decrease with increase in electric field. So d and L upon d should be negative. Now this should be negative. It is already minus, so minus will become plus. For this to be plus, mu L should be greater than mu U, right? And then we have to guarantee that P must be negative. Okay, and this term is positive and this term is negative, and overall the sum is greater than plus 1. So first condition is mu L should be greater than mu U. The mobility of electrons in lower valley should be greater than mobility of electrons in upper valley. So this now justifies this diagram also, why the gallium arsenide is designed in such a way, is fabricated in such a way that the mobility of lower valley, you can see, is higher than the mobility in upper valley. Hence we can summarize that on the basis of this Ridley-Watkins-Hilsum theory, that the band structure of semiconductor must satisfy some conditions so that it exhibits negative resistance. The first condition is that the energy difference between the lower valley and the upper valley, that is this must be, so if I call this as delta E, it must be several times greater than the thermal energy, that is KT, okay, where K is the Boltzmann constant. At room temperature it is 0.026 electron volt. This is necessary, otherwise the device will exhibit negative resistance even at room temperature, even without applying any field. So even at room temperature electrons will start migrating. We don't want that. We want when we apply the field, then only electrons should migrate from lower valley to upper valley. So this is the first thing that I can say. This delta E must be greater than KT. This is the thermal energy. Second condition is very important. That is this energy gap between the valence band and the first valley conduction band. This must be greater than the energy gap between the satellite valleys. That is also necessary, because you want to apply a field such that there is a transfer of electrons, hence they are called transfer electron devices. There is a transfer of electron from lower valley to upper valley, but not from valence band to this conduction band. So hence this delta E must be less than Eg. Okay, it's like breakdown will happen, right? Then it becomes like a conductor, because the electrons will you are applying very high field such that all electrons in the valence band, they start moving towards the conduction band. We don't want that effect to happen. We want again the transfer of electrons from lower valley to upper valley. And the third condition we already have stated, that the electrons in lower valley must have high mobility, so mu L should be greater than mu U, and they should have small effective mass. So I can say effective mass in lower band should be less than effective mass in upper valley, and low density of state. And hence you can also say that the electron velocities must be larger in lower valleys than in upper valleys. And as stated already, silicon, germanium, they don't satisfy these properties. Gallium arsenide and indium phosphide and cadmium telluride, they satisfy the properties. I don't know state of the art, okay? Those who work in devices, they may be knowing. There may be some new devices also which are satisfying such properties, but classically, and gallium arsenide is very famous one. Now, the rigorous mathematical analysis for these devices which exhibit negative resistance, they actually require a detailed understanding of high field carrier transports. Okay, so we will not delve into that right now. We'll just take one result from the famous electric field theory that relates the magnitude of current density to the charge density as well as the electron velocity. So that is given by J is equal to Q and V, where we define this respective symbols. J is the current density, Q is charge, N is the electron density, and V is the average velocity of electron. Differentiating with respect to electric field gives, and you recall one relation from electron devices that relates the drift velocity with mobility. The derivative of drift velocity with respect to electric field is mobility. So this dvd upon de, so this velocity here I will take this is a drift velocity. Now since it is equal to, I can write as q and mu n, and now see this mu denotes here, mu n denotes the negative mobility. Okay, negative mobility for gallium arsenide devices. Why? Because we know that when we are into the negative resistance we can say domain, this is less than 0, so this is less than 0, so then hence it should be less than 0. Now if I plot here the usual drift velocity and electric field, you have seen in your devices this type of drift velocity variation, but it becomes like this and then again increases. Okay, so here are some important terms which we will now define. As you can see, it is this point when the slope becoming negative. So I call this as threshold electric field. The point after which you increase electric field beyond ETH, you will get negative resistance of the bulk material. And you know that usually this line, okay, when you have a usual semiconductor, you have this mu L is equal to drift velocity by electric field, right? So this is that. Actually, your device should behave like this. Now, because of satellite valley, because of two bands in the conduction band, two values there, it exhibits this. Now, the moment it starts deviating from the linear behavior, that electric field we call as EL. Okay, and then you can see that it again starts becoming, a positive resistance device at this. You can call this as EV. Okay, and when it starts again becoming linear, I call it EU. So mu u is VD by E. Again starts becoming linear. Okay, so we are interested in this region where the mobility is derivative of drift velocity. So you might have seen, maybe instead of this, some of you may not remember it, you might have seen this relationship, VD by E is mu. This is valid for usual silicon germanium type of devices. Okay, but for these devices, two value devices, this is the how the drift velocity versus electric field variation is there. Let's take now some practical example. Suppose you have N-type gallium arsenide Gunn diode. Okay, this is now called gallium arsenide Gunn diode, which has these properties. With these particular values, we are given threshold electric field. It is the electric field after which the device exhibits negative resistance, that is 3 kV per centimeter, and the applied electric field. Okay, this is definitely, it should be greater than threshold electric field, 3.4. Length of device 12 micrometer. Doping concentration 10 per minus 14 per volume, and the frequency of operation is 12 gigahertz. Now we will first of all see what is the drift velocity. Drift velocity is also related to the frequency and the length of device, so it will be Fl. So you can find it is 1.44 in 10 per minus 5 meter per second. Okay, the second thing we can compute is current density, which is given by charge, electron density, and drift velocity. So your N is given, doping concentration, put it here, charge of electron, velocity you have found, so you can find it, it will come out to be 2.3 into 10 to the power 6 ampere per meter square. Okay, third thing, what is the negative electron mobility? So that will be mu n, and in this case it is minus of VD by E. So this will come out to be 0.423 meter square per volts. Now in next lecture we will describe how this negative resistance, this property can be used to perform a microwave generation, that is oscillation. In other words, how oscillator can be designed which will generate frequencies of the range of gigahertz and above, and also amplification, that we will do in next lecture. I will request all of you to kindly revise the devices basic concepts, not detailed proofs. Revise the definitions of mobility, drift velocity. Okay, they will be used in these lectures now again and again. Thanks.